All right. So we have Chris. Everyone here knows Chris by now, unless you are new. He usually leads off our program, and he's been kind enough to move it around a little bit today. And he's addressing a subject which, on first blush, you'd kind of go, statistics, or, who cares? But it turns out he's found something which I think, and the pattern team thinks, is really important. And I'm going to let him tell you all about it. But you're going to quickly realize that not only is Chris brilliant at visualizations, but he has found a problem, a hole, a deficit in the entire science of visualizing our data, which is desperately important, and I don't know, either it hasn't been fixed yet or will be fixed before your very eyes.
Well,
so would you like to kind of pick up from there and
sure.
Open the subject up?
Can I have my slides, please? And there they are. So my topic is on visualizing error and uncertainty. So if you've been here for the last 5, 7 years, however long I've been doing this, you will have seen me present several visualizations of large-scale data, whether it's from scientific or medical or informational sources, and we specialize in coming up with these new abstractions and mappings of that data to our visual systems. We're very visual creatures. Over 50% of our brains are for visual processing, so if we can find that good mapping, that's a great way for us to understand. However, if you look at all of these visualizations in back of me, and they're from stellar magnetism and combustion and diffusion tensor imaging and genetics, cancer genome genetics, drug pathways, there's only one of these visualizations that has a depiction of associated error and uncertainty. And why is that? And we've been spending a lot of time recently trying to answer that question, and because we see these beautiful visualizations in 3D, and is it the case that because it's in 3D and in color that it doesn't have any error or uncertainty associated with it? Well, maybe you'd think that if you saw all these. And it's really about decision making under uncertainty. This is what we do every day, all day. We are pretty bad at it. We're bad at probability. We're bad at reasoning under uncertainty and risk, but sometimes it's extremely important. This is one of the motivating cases I look at, and this is it's a neurosurgery case where we have a tumor here, and the standard way that we try to visualize this for preoperative planning for neurosurgeons is we go in and we segment out the boundary of the tumor, and then we create a three-dimensional visualization of that for the surgeon. Well, it turns out the data varies over that space, and if you look on the left side here, these are multiple algorithms for segmentation, automatic segmentation. You see that's a pretty tight bound in between those segmentation algorithms. So we're pretty confident in the estimation of our boundary, but look over here. This is the extent of the algorithms for a different place because of associated uncertainty. And so now the question is, how do we tell the surgeon or convey this information to the surgeon? Traditionally, that isn't there. It's just a hard surface that is a single surface with no error and uncertainty. But I think if this were my brain, I would want the surgeon to know that there is uncertainty, and this is in a sense a visual confidence interval of what is there. So we're trying to figure out ways that we can do a better job of adding this kind of information in. I always like a quote or two, and these are some of my favorite ones about uncertainty. Feynman, if you thought science was certain, well, that's just an error on your part. And one of my favorites, George Box, all models are wrong, some models are useful. And John Tukey, probably one of the most famous statisticians and who coined the term data science back in the 70s, far better an approximate answer to the right question, which is often vague, than an exact answer to the wrong question, which should always be made precise, which is what a lot of simulation people do. So we have been spending a lot of time in the last several years trying to come up with ways that we can encode error and uncertainty onto these data visualizations, whether they're medical images for pre-surgical planning, or their large-scale simulations from computational fluid dynamics, or their large-scale graph visualizations. How many times have you seen error bars on any infographics that you've ever seen? And the answer is probably never. And so why is that, and what can we do about it? So this is speaking of John Tukey, back in 1977, he created the Boxplot, and that is the most used visual representation of uncertainty. So if you look throughout, especially the experimental literature, experimental science literature, you'll see it's filled with these box plots. So it shows the median and the quartiles and outliers, and it's fantastic. One of the challenges with it is it doesn't, there is no, at least until recently, there is no extension into higher dimensions. And so that was one of the things that we looked at, and others have looked at it too, was, well, let's take a really successful visual representation of uncertainty and see if we can extend it to higher dimensions and other applications. And so with one of my students, Christy Potter, who is now at a Department of Energy National Laboratory, we did this thing called the summary plot, which was to start off with a box plot. There's your traditional box plot, but then we added other plots to this, a moment plot, a density plot, distribution fittings, and we called it a summary plot. And so now we have a higher dimensional entity that is in place or in addition to, for example, the box plot. And then we decided, well, that's okay, but we really need to extend this into even higher dimensions. And so we have now extended this into higher dimensions. This is a 4-dimensional data representation using an extended summary plot. It does take a while to learn how to use this. The more complicated the visual representation, the more difficult it is to understand and to get used to. One nice thing about the box plot is it's almost an intuitively obvious thing. It takes very little time to understand what you're looking at. With something that is more complicated like this, there's a learning curve. And so you see that there's a summary plot that's along the side here. So that in that dimension you get the summary plot, but then there are sets of summary plots along this axis. There's another projection down here, and then through this 3-dimensional space here. And so these are the kinds of ideas that people are coming up with. And one that I think the best is this one that was done by my colleagues, Ross Whitaker, who has been here before, and Mike Kirby, along with their student, Masha. And this was an extension of box plots into higher dimensions. They did it into what are called contour box plots. Christy and I did it into something called surface box plots. And it's a mathematical equivalent to the original Tukey box plot, but in a higher dimension. So this is flow past a cylinder, and which is a known simulation that will degrade in terms of its error and uncertainty. And you can see there, and if you can understand that box plot to the right, you can interpret, so if you know this, then you can interpret exactly the same way what this looks like. And you might think, okay, well, that's probably good for these nerdy computational fluid dynamics, but it's actually starting to have an impact in everyday people's life, because the people at the National Center for Atmospheric Research saw this. And these are the folks that whenever there's a hurricane on our East Coast, they put together these cones of uncertainty where they take 10 or so of the simulations.
I've seen it. They have a Sharpie and they go like that.
Exactly. That's exactly how it works.
Very uncertain, really.
And that's exactly how that works. And they saw this and they said, you know, I wonder if we can actually use this for the hurricane tracking instead of the very confusing sets of that. Let's have something that has a mathematical basis of something we understand, the box plot. And so 2 years ago, when Harvey and Irma came up the East Coast in Florida, one was in August and one was in September, so late hurricanes, massive hurricanes, NCAR used our box plot and to be able to see if they could better understand, their scientists could better understand the uncertainty of all of those trajectories from the computer simulation models that they were using. And if you probably can't see, but on here, these are taken snapshots, screenshots from the NCAR website. And under here it says this is an experimental Boxplot visualization. So they didn't release these to the general public yet, but they're now using these behind the scenes and in their own analysis and understanding of how these things go. And there's
Is this working for them?
and they are, yes, and so they're using this, they're augmenting this with additional techniques for uncertainty analysis and visualization. One of the interesting questions is that would this be any clearer to the general public, because they probably don't know what a boxplot is.
But the officials are already using things like this to decide whether it's a voluntary evacuation, mandatory evacuation.
I'm not sure about that. I think that they're using this to better understand how they can understand the uncertainty of the computer models.
Yeah.
But I can tell you a fun story is that, so Masha was the PhD student who led a lot of this work, and she is now an assistant professor of computer science at the University of Florida.
I knew you would say that. There she is right there.
And she is probably one of the few PhD students who could use her dissertation work in a really important way, which was to decide whether she should evacuate, and she did, and it was the right thing to do. And so these are the kinds of ways in which we think we can start using and extending the statistics of uncertainty and error, but to higher dimensions. And one of the things that people, when we talk about uncertainty, one of the things that people often come up with is, when you represent this, well, why don't you just make it fuzzy or blurry to this? And it does definitely have its applications, but there are some restrictions. So this is some work from Russ Taylor, who's a professor of computer science at UNC. And one of the things that he's showing here is on the left, this is a parallel coordinates visualization, which is high dimensions. So every single one of those lines is a dimension in the problem, in the data dimensions. And parallel coordinates is a way that we can look for features and clusters of information. And so you might look at that parallel coordinate visualization here in the upper left, and right along this particular axis, you see, wow, there's a lot of stuff going on right here. So that looks like that's a very, very interesting and important area. And then they added uncertainty into the equation. And it turns out that while that was so highly correlated over here, that actually it's very uncertain data, and so it's very unlikely that there's anything important going on there. But it was just so easy to mislead yourself and others, because there's no depiction. If you just took the raw data without the associated uncertainty, then you're going to make some very serious mistakes. Bottom one is another really good example of scatter plots. Scatter plots are the most used visualization of any kind ever. So we did a survey. The visualization people wanted to know, like, what is the most used visualization representation of data? And the answer is the scatter plot. You get a bunch of data and you plot it, and you just throw it on the screen. And people look at this and they do these scatter plots, which is in this bottom left here, and they're looking for trends. And so they're looking for trends, and you might say, oh, this data is correlated. It might have there might be a slope of that axis along this one. And then they also look for outliers. Well, that's obviously an outlier here. And then you actually start looking at, well, let's put some of the uncertainty into the data, and what does it start looking like? And the next two images that you see there are different representations of with the uncertainty that's in there. And it no longer, the outlier goes away, and so that was good. But it also doesn't look like it's like this linear slope. It looks like it's much more clustered into a center part. One of the things, though, about this is that whenever we're using this kind of fuzziness, blurred effect, is that we don't have a good quantitative feeling, understanding for that. So I use the analogy of fog, where we know when it's really foggy and we know when there's not fog. We're not really good at saying, oh, it's 17% foggy out today, or 34% fog I see. And so there's been studies, psychological studies of uncertainty where they have tried to use this as a metric. And basically, people understand when the uncertainty is high, and people understand when the uncertainty is low. There's some people that can understand the uncertainty in the middle, but not a lot. So we're not very good at it. So we're trying to figure out ways to encapsulate and not go overboard in terms of too much detail, because our brains are not so good at this kind of probabilistic reasoning of, well, that uncertainty is that amount. So we're kind of trying to keep it at high or low that we have in there. So we've extended this now to scientific and other visualizations. This is a three-dimensional visualization of a tooth. So we can do a lot better than your dentist when you go in to get your tooth visualized. We created something called three-dimensional transfer functions. And we've now been able to adapt that technology to not only visualize the data, but show its associated uncertainty, so that pair of brain scans, visualizations on the right, over here, what you're seeing is the structure, but you're also seeing the confidence interval. So it's representing the 90, 95th, and 98th% confidence interval. We can also do sensitivity to a particular variable and other mappings that we have. So ways to show structure, but also the associated uncertainty that we have along the way. And now we've extended this to even higher dimensions, and this is one of the ongoing challenges. This is some geoscience data. And this now is a 6-dimensional transfer function. Down here is the 6 dimensions in parallel coordinates. And this shows the associated uncertainty in the seismic imaging here. What happens, though, is that as you increase these dimensions, and we keep increasing the dimensions of our data, is that it becomes much, much harder for us to design effective user interfaces. Mm-hmm. We are good at visualizing 2 dimensions. Some people, not all, are good at visualizing 3 dimensions. I was really surprised because I'm pretty good at 3-dimensional visualization, but there are tests that you can have, or people, they are very lousy at 3-dimensional visualization. Really? Not too many people are good at visualizing 4, 5, 6, 7, and higher dimensions. And so once you go beyond 3, really, you have to come up with new abstractions and new ways to interact. And this is a huge open research problem in human-computer interaction and visual analysis, is how do we find that abstraction that can then do the data reduction, the visual data reduction down into some space that we can actually understand, because it's so easy to overload us, our visual systems and our capacity to reason visually once we get beyond 3 dimensions.
So I was kind of hoping at this point you'd solve that problem, because as you may remember during our splash video from Pattern, the last thing we did was show 27 dimensions of breast cancer discoveries.
Yeah, right.
And it's very, a lot of stuff going on there.
And so this is absolutely an open research problem. There was a Nature Methods article just last year, which was titled "The Unsolved Problem of Uncertainty Visualization." And so there's an increased interest in the field, where more and more visualization and other researchers are encoding uncertainty. One of the challenges that we have is that, as you can see with any of these visualizations, there's already complicated data we're just trying to understand. So just visualizing the structure of the data itself is already challenging.
That's what I was going to say, just the 27 dimensions,
and now we're going to overload that with uncertainty. And what we found is that when it doesn't take much to start overloading people to where they are distracted by the uncertainty, or now they're concentrating on the uncertainty, and we're like, no, concentrate on the certain parts we know about, but know that there's this uncertainty here when you're doing your reasoning. So you have to be very careful about overdoing the abstractions and the mappings into the visual space. So you can start having structure and color and other things, but once you get beyond a few things, our brains go bloop.
If you were to apply this to a process, right? So far there's like static information with many dimensions.
Yeah.
So let's say there's a process.
Yep.
And there are 6 steps to the process.
Yep.
Maybe you're making something, you're manufacturing something. and or you're discovering something. And so you go through step one. Okay, that was a pretty certain thing. That was only 2 or 3%. And then step two is pretty good, pretty tight. We've done that a long time. Step three, it really goes crazy, right? And there's 50% loss rate and whatever, and certainty. And you bring it back down, and by the end, you're back to like 2%. You think, well, this is, the last one was 2%, so we're in good shape, right? But in fact, what happened was the whole thing blew up in step three, and the cumulative effects of all those uncertainties has got to be wildly large, right?
That's right. And so figuring out and actually doing that process is very important, because anytime you're doing anything with data, and oftentimes people are taking data and doing this data triage and data handling, where they're taking the data and doing data reduction, they're doing filtering, they're doing all kinds of stuff to the data. Step. And most people don't even know that that's there, but they're introducing error and uncertainty every time along the way. And so you need to analyze that pipeline and figure out where you're introducing the error, how much, what's the estimation of that error, and then be able to certainly know where you have the most error and try to mitigate that and to understand that in terms of the overall process. Getting back to the time thing, one of the things that we're also using is almost all of these are time-dependent problems, and we're pretty good at looking at, so using animation as watching error. So there have been some studies of, you're watching, it's like, whoop, there was something there. And so we're good at noticing those blip differences. And so that's one way that we can understand in a process of what there at least has been error, and then localizing that to go back and try and figure out what was going on.
Right.
Another thing that's really interesting is, so there's all this issue that, in addition to the just all the techniques that we're looking at, we go even fundamentally back just to our visual perception. It turns out that most of the computer graphics physics that we use every day for all of the graphics and visualizations is based upon many-year-old technology back in the day when computers were not that powerful. So they weren't, in the beginning, they weren't solving Maxwell's equations for light and scattering and shadows because they couldn't. And so there were all these approximations made, simplified models of light and shadows, and that were used. And those are so ingrained into the computer graphics pipelines that every graphics engine that's out there and software that's out there still uses these approximations. And now we have the computer power to be able to solve Maxwell's equations for real. And this is an example. So this is a visualization, one-time institute of a complicated fluid mixing. And this is the standard. If you download any graphics software or visualization software, this is what it's going to look like. Now we've done it with Maxwell's equations on the right. Did you see the difference there? Oops, can't see that one yet. So that's now. And now the one on the right is with Maxwell's equations.
Do you mean Maxwell's equations for light?
Light. And so what we're doing is now we're following the scattering of all those photons moving around. And what it does is you can see the shadows a lot better because of all the reflecting rays that are bouncing around inside on the surfaces. And we are very, very tuned to shadows and associated with that with depth. And so we get a much, much more understanding in terms of that if we now do this global illumination. And this next one was just recent.
So you're showing that because light is a lateral wave, how that light as a lateral wave impacts these various surfaces.
It's basically light bouncing around in there, and from all of that, it's going to give you, this is, the one on the right looks like it would if you had a light source, and that was a physical model, and you were going to be able to look at it.
Yeah.
And the one on the left is using the computer graphics technology that's been around for many years, and it doesn't have a full explanation or representation of light. And
so knowing more about the nature of light allows you to make a more differentiated picture.
That's right. And what's funny is that when we tried to publish this, we got a lot of feedback basically saying, well, you have to show that this is better than what we've traditionally been using. And if you're from the physics point of view, usually it's like, well, here's the true physics, and we're going to try and sell you on our approximation. And the computer graphics is like, well, here's the approximation we've been using for 20 years, and we're trying to sell you on, well, here's the actual physics that's going on here. And they're like, people are like, I don't know, we've got a lot of infrastructure that we'd have to
Well,
change.
that's what I was saying. But you're really saying, here's the stuff you're using today,
that's right.
and that doesn't so good, it turns out.
Yeah, and you're going to have to change a lot if you
Yeah,
want to use
right,
this.
yeah.
And
This is another example of flow. On the left is traditional visualization software standard. That's what's used by 99.9% of everybody when they do their visualizations. And then the one on the right is now with global illumination, where we're actually solving the light equations. And most people, even not trained scientists, will look at that and say, well, I think that looks interesting. So why is this hard? This is a paper that was just published by Jessica Hullman, who's at Northeastern University. And what she did was she combed 86 publications, recent publications on uncertainty visualization. And she found that there were 372 different ways that people had done the uncertainty visualization. And she decided to make a visualization of the uncertainty and the map. And so what you're seeing here is a map of all the different ways from these 86 papers and the 372 different ways that people had uncoded and reasoned about uncertainty in their visualization. So what jumps out at you is that there is no one size fits all. Unfortunately, there isn't a Tukey Boxplot that will work for everybody. And they're all different kinds. It's very application specific. It's very dimension specific. So we've got a long way to go. I'll skip over that because I see we're at 0 here. And what I'll end with is that since it is the 50th anniversary of ARPANET, the internet, I wanted to make sure and put a plug in for these guys at Utah. Number 1 and 2 are David Evans and Ivan Sutherland, who had one of the original ARPA centers for graphics back then, and we were the 4th node on the internet. Also, it turns out because of Ivan, it's the 50th anniversary of virtual reality.
Is that right?
Yeah. We just celebrated this at SIGGRAPH with Ivan, who turned 80 this past year. The father of computer graphics, but also the father of virtual reality, and they showed the first head-mounted display that he created back 50 years ago. So this year is an amazing year for anniversaries of technology. So it's interesting that VR and the internet are same age, and also we see so much interest in revolutionizing both.
Right.
Yeah.
Well, so we have the founding director, and now just I think this year you've moved out of that position. But
yes, after 30 years.
But if you go to Chris's office, which I've done a few times, the faces on the wall, which we were just looking at.
Yeah.
I mean, it's incredible.
Yeah.
You all probably know that the Ski Institute is the best visualization institute in the world. But when you see these names on the wall,
and these are the people I learned from. These are John Warnock is one of our graduates, founded Adobe. Ed Catmull's one of our
Pixar.
Graduates, president
Jim
of Pixar.
Clark.
Jim Clark, SGI.
Alan Kay,
Alan Kay did
Nolan Bushnell.
Object. These are all our graduates, and I got to learn from all of these guys, which was really amazing.
Yeah, incredible. Well, but you are going to tell there's a punchline, right? Like you're going to tell us the real answer now, like it's doable and you solved all these problems.
It's really an ongoing problem. And one of the things that is really interesting with all of the advent of machine learning and everything, the same question applies, because when you get an answer from machine learning, it doesn't come with a confidence interval.
Right.
And this is a big deal.
Yeah.
And we need to not only do we need to do this for the visualizations of simulations of traditional medical imaging and information graphics and things, but we also need to do this for the whole field of machine learning in terms of it's not just an answer. We need those confidence intervals in order to make that segmentation of the brain I was looking at. The way that they evaluate segmentation algorithms clinically is they have a number of experts, radiologists, and that go in there and they hand segment that, and then they get an average and a confidence interval, and then they compare the algorithm to that. And it's what we need to do. We need something similar with machine learning, where there's a confidence interval on that result that we get from machine learning.
Right.
So we have a little ways to go, but it's really exciting because there's all kinds of and new research that
Yeah,
we need
well,
to tackle.
we just hired a brand new person at Pattern who's going to be working on visualization, and Chris met her yesterday. So we're on the case here. We're going to
That's
figure this
right.
out. Thank you.
That's
very
right.
much.
Oh, yeah. Well, thank
Appreciate
you. Thank you.